Hello, everybody. This is Professor Ma, and this is the summaries on the sections on parametric equations. Mm. Let's start out with before we had a topic on something called linear motions. That is, if I have a point that's going back and forth on a straight line, and we can set describe the motions using a function's distance from 0, and we can call it x of t. And suppose this is the x axis. Okay. As time goes on, then xt describe the positions of the point, and we can take derivative and get the velocity of x prime t is the velocity. Then the second derivative is the accelerations. Okay, and from there we can deduce the motions of the point. For two-dimensional situations, well, suppose now we have the point that's traversing is going along a path, a curve. And then to describe the motions, and so what we do is then we go from the linear motions in one dimension, now we put it into two dimension, upgrade to two variables. That is, in the x components, we have the xt, which is the of course the linear motion along the x-axis, and then of course project onto the y components the linear motion along the up and down, the y sub t from here to t. Okay, as the point goes along the curve, then at different time t, it will occupy different positions. So this is the x and y are functions in t, and the set of two xt and yt, we call this set a set of parametric equations describing the motions. Okay, and the key point here is we're describing the motions, which really is the based on the variable, which in this case we call parameter, the time t. Okay, so here's an example. And from t0 to 9 seconds, the points move along the x components square of t, and the y component t minus 4. So we plot them. Okay, so t0, that's where the location of the point is, and take a snapshots, and after 1 second, then that's where the position of the point is. It's plugging, and then that's after 4 seconds we take a snapshot, and that's the point. And after 9 seconds we finished up there. So basically it's a very short videos of a point going along the curve and stop. Okay, but it's a basic for it's a basis for animation actually. If you like, you can write a program to actually animate these things easily. Okay, and the positions has the motion has an orientation, has a directions, and the direction of the motion is the direction where it is heading as t increase. Okay, and in this case, if I put a negative sign in front of the y, then you were describing a opposite motions in this setup. The track, the trail, it maps out. Okay, it's a curve, and I can, if I don't want to use the variable in between variable t, I want directly a formula between x and y, then in this case it's very easy to get that formula, and we basically solve for the t. Okay, in one of the equation, doesn't matter which one. Okay, I use the x ones over here. Then t can be replaced by x squared, and which we will do and put this x squared into the t for the other y. So we'll get y x squared minus 4. So this is part of a parabola. Okay, so so this is a excuse me. So we also say this is a parameterization of these segments of this curve. Okay, this is a particular parameterization of this segment because it describes a particular motions. Okay, a particular time, a particular place. You know, there are other parameterization and the describing motion. If the motion is a different motions, you know, it doesn't go some in these particular fashions. So there are a lot of different parameterizations. For instance, we a lot of time we use theta, the angles as a parameter. The parameter doesn't have to be time. We can kind of match time as something rotate. The angle, we call that theta, it kind of the same as time. You know, you want to view it this way. And so first of all, the track for this parameterization, it's easy to see the square sum formula give me the track is the circular track of radius 3. And where does the motion start? Well, start with the point 0, right? And notice any formula that involves only sine and cosine and trig formula, then they will have 2 pi period. So formulas of the trig parametrize formulas. Okay, well, parametrization only involving trig formulas and constants. They all have 2 pi period. Okay. So in this case, a 0 theta is the red point position. When theta is 2 pi, it went up the same locations, okay? And as pi over 2, when you start moving, when the angle increase to pi over 2, that is going around clockwise. So basically this, we can say, oh, this parameterization describe this red point go around the circles and to the blue point, then to the green point, and then go back. Okay, from 0 to 2 pi. And following are the parametric formulas for circles. Okay, and so basically it could be plus minus cosine versus plus minus sine. Okay, one set. Or could be plus minus sine for the x and a plus minus cosine for the y. Okay, the sine, and there are one. Okay, there are 8 variations here. It could start at 4 different positions, right? The 4 cardinal points, and the pluses and minus goes one way or the other. So that's 8 different descriptions here. Okay, and for ellipses, basically you just change the axial length. I mean the length of the radii of the circle, which turns into ellipse. Okay. For any functions, if I start with a function, then there's what we call a standard parameterization. So if I want to view the x component as time, okay, and as y component as the function f of t, then these set of parameterizations, we call these standard parameterizations. Okay, so basically we are treating this point, this is t is same as x as it goes along, and then the points that it travel along the curve. Okay, and so on, so on. Okay, it's going up and down. Okay, so here's a standard parameterization of y equal to x squared, just t squared. And how do we calculate this slope for parameterized curves? Okay, suppose I have xt, yt. Well, it's just basically it's just the ratio, it's just fractional ratios. Okay, instead of, remember the key point over here, going back again, is that dy is delta y over delta t. Okay, oops, sorry, delta y, and the dx is delta x, and if there's an intermediate variable t, and so that's y is changed by t, so then x change according to t. Then in terms of, suppose these are all very small positive number, then I can just flip it over, and then this is then this is that. But on the other hand, they are small positive number. They get, each one gets closer and closer to the things we call dy dt divided by dx dt. Okay. So individually, this that's what we are calculating. So we got this formula. So by the way, again, why dy dx? What, I mean, I know people say, why do I can't calculate dy dx? Oh, dy dx on the xy coordinate, dy dx is the slope. Okay, this is dy, this is dx. Okay, so that's what we're calculating. So you'll give you the slope. Okay, it give you the change on the graph of the ratio between x's and y's. Okay. And it is calculated via the ratio of to the x, I mean, to the t of the y, and to the ratio of dx dt. Yeah, it goes to the t. Talking too much, but here. So here's a set of parametric curve. So first, let me recover the algebra versions. So this is easy to check. I'm going to take cube root of something and then square it. Okay, I can take x to the cube root. So positive, then I'm going to square, make them positive. That's why you get the both sets on top, y positive. Okay. At that particular time, when is the point will be at the point minus -a4? Well, gee, just plug it in, say, well, -8 will become x, well, x is -2. So t is -2, sorry. Oops. So find the slope at that point. The slope at that point is dy dx. But that will be evaluated through two ways. I can do a dy dt, dx dt, or I can calculate, if I have this formula directly, I can calculate dy dx or dy dt, dx dt. Okay. So here's dy dt versions. Okay. And if you take dy dx evaluated at point -a, plug in, you get the same answer. Okay. Arc length formula. The derivation of this formula is pretty much straightforward. If you go back to 265, the arc length formula for curves, it can easily just get it out of that same versions. Okay, how do you pull out the denominator? Okay, in algebra. Okay, and again, in order to integrate these, arc length is not easy. In general, it's not easy things to calculate. Okay, so for the problem that will work out, the x and y has to be kind of specials, and then you can take the square root and things all comes out nicely, like this one. Okay, if you say why this strange power, like O divided by 3 and 2, well, it's because the algebra work out. You can pull a t out, and then we can use integration by substitutions. Okay. So, and then this is the answers. Okay. Again, on the homework, you will see a lot of problem with a kind of strange power. Okay, that's because we need to have the integral that comes out nice and nice and easy. Okay, pretty. Okay. Okay. So this is basically excuse me. This is the same. This can confirm that if I plug in for the case of circle, I'm going to get these nice easy equations, and 1/4 pi, which going around twice. Okay, so that's it. Until next time. Bye-bye. Where is it? I don't want to stop share.